Hey Chem Coders, welcome back to the channel where molecules meet Python. Today we're tackling not one, but two projects, demonstration of Boyle's law and empirical formula calculations. We'll go line by line, see how lists and tuples shine, and even run real examples like glucose. Buckle up, this is going to be a fun ride. Here's our experiment setup. Temperature, 273 K. Moles, 1 mole. Volumes, 1, 2, 4, and 8 liters. Each item is a tuple, label, and value. Tuples are immutable, perfect for fixed data. We pack them into a list and we will loop through them. This prints the title and fixed parameters. Experiments 01 grabs the temperature value, 273.0. Experiments 11 grabs the number of moles, 1.0. Indexing into lists and tuples lets us grab values easily. This defines how our columns look in the table. Volume with width 4, precision 1 decimal. Pressure width 6, precision 2 decimals. Product P times V with width 6, precision 2 decimals. Later we'll use list comprehension and unpacking to build an output table. Here we build the header row. Each column name is centered, width. We join them with tabs, then we print a dashed line for style. List comprehension is used here. List F string, name, width for name, width, and prec. In call specs, it's a compact way to build a new list from call specs. List unpacking happens in the loop for name, width, and prec. In call specs, each tuple in call specs is unpacked into 3 variables. The underscore prec is a placeholder. It keeps the unpacking order correct, but signals we don't actually use this value. Python convention says underscore equals ignore me. This creates a format string for the data rows. Each number will be right-aligned, greater than, with the specified width and precision. Again, neatness counts. Now the fun part. Computed results will be collected in results list. Here's the loop. We skip fixed params, temperature and moles, and we loop through volumes only. Experiments 2 does that. If real experimental data is available, we will read them. Instead, here we calculate pressure with P equals nRT over V for each volume. Then we compute P times V and assign it to product. We append product to a results list. That's why we use a list instead of a tuple. In the last line, results -1 means the last element, the one we just added. Asterisk results -1 is argument unpacking. It takes the tuple, V, P, product, and unpacks it into 3 separate arguments for format. So instead of passing the whole tuple, we pass each value individually to match the 3 placeholders in data format. That's why the table prints correctly. Finally, we show the constant P times V. Boyle's law confirmed. No balloons harmed. Python proves Boyle's law without popping balloons or cleaning glassware. And, unlike your lab partner, Python never forgets the goggles. We squeezed balloons with Boyle's law. Now we're crunching numbers to find empirical formulas, the simplest whole number ratios of atoms in a compound. And yes, Python is going to do the math for us, so you don't have to wrestle with fractions like 1.33 or 1.25 at 2 a.m. before your lab report is due. Here we define a tuple of atomic masses. Tuples are immutable, like the periodic table itself. You don't just change hydrogen's mass because you feel like it. Each tuple has the element symbol and its atomic mass. Empty lists ready to collect user input. Lists are mutable, so we can keep adding. Here comes the interactive part. We ask the user how many elements are in the compound. Then, for each element, we ask for its symbol and its mass in grams. We append those values to our lists. So if you type in C, H, and O with their masses, Python builds your dataset. Before moving on to the next part, notice the .capitalize method applied to the element symbol input. Why .capitalize? Well, users might type symbols in lowercase, like lowercase c instead of capital C. .capitalize ensures the first letter is uppercase and the rest lowercase. This matches the format in our tuple of atomic masses. Without .capitalize, the program wouldn't recognize lowercase c as carbon because Python is case-sensitive. Why not use .upper function? .upper would make all letters uppercase. That works fine for single-letter symbols like C or O, but it would break two-letter symbols like CL. Chlorine's symbol is CL. Only the first letter is uppercase, the second is lowercase. If we used .upper, CL would become all uppercase CL, which wouldn't match our stored tuple. So .capitalize is the correct choice. It keeps CL exactly as it should be. Now we convert grams to moles. We look up each element's molar mass from our tuple, then divide the given mass by molar mass. Voila! Moles of each element. Chemistry trick! Divide all mole values by the smallest one. This normalizes the ratios so the smallest becomes 1. That's how we get relative proportions. This function is the hero of the script. It handles those pesky fractions like 1.33 or 1.25. We define a function called simplify ratios. It takes in a list of ratios like 1.33, 1.0. The arrow list float is a type hint. It tells us the function will return a list of floats. It is helpful, but it is not mandatory for a function to have a type hint. Line 2, factors equals list range 1 to 12. We create a list of multipliers, 1, 2, 3, etc. Why? Because sometimes ratios like 1.33 can be turned into whole numbers by multiplying by 3. 1.33 times 3, approximately 4. This gives us a set of possible multipliers to try. Line 3, tall equals 0.05. Tall means tolerance. When we check if a number is close to a whole number, we allow a small margin of error, 0.05. Example, 1.99 is close enough to 2.0, so we accept it. Line 4 through 5, we loop through each multiplier in 1, 2, 3, etc. All whole equals true assumes optimistically that multiplying will make all ratios whole numbers. If we find even one that doesn't fit, we'll flip this to false. Line 6, test equals r multiplied by mult for r in ratios. This is a list comprehension. It multiplies each ratio by the current multiplier. Example, if ratios equals 1.33, 1.0, and mult equals 3, then test would be 3.99, 3.0. Lines 7 through 10. We check each value in test. Round, val, gives the nearest whole number. Abs, val minus round val, measures how far the value is from that whole number. If the difference is bigger than our tolerance, 0.05, then it's not close enough. We set all whole equals false and break out of the loop. Lines 11 through 12, if all whole, return round r times mult for r in ratios. These say if all values pass the test, they're close to whole numbers, we return the rounded. Example, 1.33, 1.0 with multiplier 3 to 4, 3. That's our simplified integer ratio. Line 13 through 14 means if none of the multipliers worked, we fall back to normal rounding. Example, 1.2, 1.0 to 1, 1. Not perfect, but better than leaving fractions. This function is the fraction fixer. It's what makes empirical formulas look neat and professional instead of messy decimals. So 1.33 becomes 4/3, which simplifies to 4 atoms versus 3 atoms. Chemistry teachers everywhere rejoice! Let's try glucose with masses C equals 40.0 grams, H equals 6.7 grams, and O equals 53.0 grams. If we run this, mole ratios normalized equals 1.005 to 2.007 to 1.0. Integer ratios equal 1 to 2 to 1. The empirical formula is approximately CH2O. Glucose's molecular formula is C6H12O6, but the empirical formula is CH2O. Now let's see a tricky case. If the percent composition is 15.87% C, 2.22% H, 18.50% N, and 63.41% O, because percent composition is directly proportional to the masses of the elements, a 100-gram sample contains 15.87 grams of carbon, 2.22 grams of hydrogen, and so on. After running the script, you get the raw ratio 1.001 to 1.668 to 1.0 to 3.001, and integer ratio is 3 to 5 to 3 to 9. So the empirical formula is C3H5N3O9, and it is nitroglycerin. Fractions at 2 a.m.? No thanks. Python looks at 1.33 and says, "Relax, I'll fix it." It's like having a math tutor who never sighs. In this single tutorial, we used tuples for fixed data and lists for mutable results. We proved Boyle's law with a neat table. We built an empirical formula calculator that handles both easy cases, glucose, and tricky fractional ratios. Wrapping up, Python plus chemistry equals fewer headaches, more insights. And remember, constants are your friends, unless they're exam deadlines. Smash that like button if you enjoyed mixing science and code, subscribe for more chem coding adventures, and drop a comment. What's scarier, debugging Python or balancing chemical equations? Personally, I think both can make you cry, but at least Python doesn't smell like sulfur dioxide.